Alright folks, in this video we're going to discuss the second topic of chapter 5, Lewis structures. This is going to be a big topic and we will have 3 videos for this one. And in this video we're going to focus on how we draw Lewis structures if you have a formula. In order to do that, we do need to follow some procedures. We will use examples to demonstrate how we follow those procedures to come up with the right Lewis structures for compounds. Let's see the first compound, CH4. Okay, this one is relatively easy, but it's going to be a good example for you to start. The first thing that we need to do is write the correct skeletal structure for the molecule. Well, 2 notes. First one, central atom should be the atom with less electron negativity, and the second, hydrogen is always terminal or surrounding atoms. Okay, so now as you notice that this one has 2 elements, carbon, hydrogen. So as the second note shows you, the hydrogen should be surrounding atoms. So that means carbon should be the central atom, and you have 4 hydrogens around the central atom. Okay, and we are not done yet for step 1. Step 1 says the skeletal structure. You find out the positions for those 5 members. Well, the next thing you need to do for step 1 is to draw single bond for each pair. Okay, well, why do we draw a single bond? Well, think about it. Those hydrogens and carbons, they are going to stay together in this compound, right? And in order to do that, in order to stay together, they need to have some kind of bonding interaction. So we always start to show this kind of bonding interaction. We always start from a single bond. Okay, later on we can come up with the double bond, triple bond, or something like that. But a single bond is the simplest chemical bonding information between these non-metal elements. Okay, so drawing single bond, it's gonna be the second part of step 1. Now the skeletal structure is finished. We can go to the step 2. Calculate the valence electrons for the Lewis structure. Valence electrons, if you happen to remember what that is, if you know the electronic configuration, then you will know the valence electrons. But another way to do this is check the group number. Well, carbon, it's in group 14. 14 minus 10, then you will have 4 valence electrons. Okay, 2s2, 2p2, right? Now hydrogen, we know that it has only 1 valence electrons, so 1 valence electrons. Because you have 4 hydrogens, so we multiply that by 4. So total you have 8 valence electrons. Well, this 8 valence electrons will be used by us to construct the Lewis structures, including these single bonds. Okay, keep that in your mind. Now this is the note for step 2. If you are dealing with the polyatomic ions, then you need to either add the negative charge or subtract positive charge. We will do that later on when we talk about some other examples. Number 3, distribute the electrons among the atoms. Okay, we have 8 electrons. Now, how many valence electrons we've already used when we construct the skeletal structure? That's the first thing you need to consider. The second thing is when you distribute the electrons for those members, okay, those atoms, you need to start from the surrounding atoms. Okay, the reason is usually those surrounding atoms, they have higher electron negativity, so they like electrons, so you want to make them happy first. Okay, so if you follow this instruction, check those 4 hydrogens. Hydrogen follow duet rule. In other words, if you have 2 electrons for each hydrogen, then it's happy enough. Now for this hydrogen, as you notice, it's sharing 2 electrons with carbon, so This hydrogen has 2 electrons already. This hydrogen has 2 electrons already. Remember, one single bond, one single covalent bond means or represents 2 electrons. Okay, this hydrogen shared 2 electrons to form a single bond. These two share 2 electrons. So all of the 4 hydrogens, they are happy. They have 2 electrons. Satisfy the duet rule. Okay. Now, if you check the carbon, how many electrons does carbon have? Well, you have 2 here, 2 here, 2 here, 2 here. Now, that means the carbon has 8 electrons. Okay. Well, carbon, hydrogen, all 5 members are happy. And then the last thing for step 3 is to check whether we still have extra electrons left. Well, you've already used 8 valence electrons for the 4 single bonds. That means that you don't have any extra electrons left. All right? So for step 3, and that's it. Now, step 4, if any atoms lack an octet, then it will form double bond or triple bond. Well, this procedure will not be applied for this methane molecule because right now everybody's happy. You don't need to form double bond or triple bond. Okay, so well, this is the loose structure of methane molecule. All right, now the second example, let me write it here, would be carbon dioxide, CO2. Okay, now again, start from the first step, CO2. Write the skeletal structure. We have carbon, oxygen. Well, if you happen to remember the trend of electron negativity across the same period, carbon is on your left side of oxygen. Therefore, carbon has less electron negativity than oxygen. So according to this note here, carbon should be the central atom. All right, and 2 oxygens should be on 2 sides. All right, skeletal structure, like I said, that's a single bond for each pair. All right, so this is step 1. Step 2, calculate the valence electrons. Well, carbon, 4 electrons, oxygen, 6 electrons. Of course, since you have 2, then you multiply that by 2. So that will give you 16 valence electrons total. All right, we've already used some of them, and particularly 4. Okay, we've already used the 4 of them, but we still have more electrons. So let's go to step 3, distribute the electrons to make those atoms satisfy octet rule. Well, we again, like we mentioned here, you start from the surrounding atoms first because oxygen has higher electron negativity, it likes electrons. It wants to get 8 electrons first. All right. Now, if you notice that these 2 electrons are shared by carbon and oxygen, in other words, this oxygen has 2 electrons already. That means as long as we give it 6 more electrons or 3 pairs, okay, then the oxygen would be happy. Now you have 8 electrons for oxygen. By the way, for those 2 dots, we call it lone pair. Okay, the lone pair means those 2 electrons will just belongs to the oxygen itself. Will not be shared by the oxygen with other atoms. Okay, so lone pair. Well, the oxygen, this one is happy. How about the other oxygen? Again, we give it 6 electrons. Okay, and then you can see both the oxygens are happy. Both of them have 8 electrons. Now let's see how many electrons do we still have. You have 8 electrons for oxygen. Okay, 1 pair, 2 pair, 3 pair, and then the 4th pair. So total 8, and a total 8 on this oxygen. So that means we've already used all 16 electrons. We do not have any electrons left. But if you check carbon, carbon is not happy because it has only 4 electrons. So it needs more electrons to satisfy octet rule. Okay, so apparently that we have to do step 4 in this case because carbon lacks an octet, so we need to form either double bond or triple bond. Okay, all right, so how do we do it? Well, we will ask this oxygen to share one pair to form a double bond. Okay, all right, double bond. And still carbon right now is still not happy because it only has 6 electrons. So we ask this oxygen to share a pair. Okay, so form another double bond. Now if you double check, carbon has 8 electrons now. Everybody's happy, and then that's the loose structure of this compound. Let's see more example. Third one, HCN. Okay, now you have 3 elements. How do we start? Well, it doesn't matter how many elements you have in the molecule, you always follow those rules. Central atom with less electrons, hydrogens surrounding atoms, hydrogen surrounding atoms. Okay, for carbon and nitrogen, like we did for carbon and oxygen, carbon, nitrogen, they are in the same period. Carbon is on your left side of nitrogen, so carbon has less electron negativity than nitrogen. Therefore, carbon would be the central atom, and nitrogen would be another surrounding atom. And skeletal structure means you have 2 single bonds for, the 2 pairs. Okay, this is a good start. Now, the second step calculates the valence electrons. All right, no problem. Let's see. Hydrogen, 1 valence electrons. Carbon, 4 valence electrons. Nitrogen, group 15. So 5 valence electrons. So total you have 10 valence electrons. All right. Now, again, we've already used some of them, but we still have more. So let's distribute these electrons to nitrogen and hydrogen to make these surrounding atoms happy first. Okay, we are in step 3. All right. Now, hydrogen, as you notice, it's happy already because it has 2 electrons. But nitrogen is not happy. It has only 2 electrons. Nitrogen needs 6 more electrons. That's okay. We'll give it a 6. Or 3 pairs, 3 lone pairs. Okay. By the way, the lone pairs, let me write it here. So it's lone pair. Okay. It's not shared by 2 atoms. It belongs to just 1 atom. All right. Now, as you notice, nitrogen 8 electrons. Hydrogen 2 electrons. And how many electrons do we still have? You have total 10 available for you to use. You've already used the 2 plus 8. Well, you've already used all 10 electrons. But carbon is still not happy, right? Like the carbon, like we did in carbon dioxide, we have to go to step 4 to form double bond or triple bond. Let's see what will happen in this case. Well, first thing is, hydrogen does not have any electron pairs for you to share, so double bond or triple bond can only happen between carbon and the nitrogen. So we ask nitrogen to share 1 more pair. Okay, so form a double bond. But still, it's not enough for carbon because it only has 6 electrons. So how about we ask nitrogen to share 1 more to form a triple bond? All right, now you see carbon total 8 electrons. 2 electrons between carbon and hydrogen, 6 electrons between carbon and nitrogen. Triple bond represents 6 electrons. Double bond represents 4 electrons. Okay, so and this is the loose structure of HCN. All right, now next one. Example 4, NO3 minus. Well, you notice that this is charged. Okay, so this one we are gonna do this part. Okay, but no matter what the molecule or ion is, you always start from the very beginning. Skeletal structure. Well, nitrogen has less electron negativity than oxygen, so nitrogen would be the central atom. So nitrogen and 3 oxygens here. And the skeletal structure, that means you start from a single bond. And since it's a charged ion, so we draw a bracket and then put the charge outside the bracket to represent that this is an anion, or this is an ion. All right, now we go to second step, calculate the valence electrons. Nitrogen, group 15, 5 valence electrons. Oxygen, 6 valence electrons. Of course, you have 3. So multiply that by 3, so you have 18 valence electrons. Now, be careful. We said that's the note of step 2. If the ion is anion, negatively charged, then you need to add the charge when you count the valence electrons. Why is that? The reason why it's negative charged, it's because this NO3 has to get 1 extra electron to get stabilized. You don't need to care about where that extra electron comes from. Okay? As long as you know that this negative charge represents 1 extra electron and it needs to be added in the valence electron count, then that would be good enough for this topic. Okay, I want to make a note here, plus 1 extra electron. Where does this electron come from? That comes from that -1 charge. All right, now if you add them together, 24 valence electrons. Okay, well, now it's time for us to, again, we've already used some of them, okay, some of them, but we have extra. So let's make sure that everybody's happy. For oxygen, like we did for carbon dioxide, we need to give each one of them 3 pairs to satisfy octet. Okay. All right. Now let's see how many valence electrons we've already used. This one 8, oxygen is happy. This one 8, oxygen is happy. This one 8, oxygen's also happy. So 3 times 8, 24. We've already used the 24 valence electrons. We don't have any extra electrons to make nitrogen happy, but it needs 2 more electrons to satisfy octet rule. Therefore, one of the oxygen will share a lone pair to form a double bond. It doesn't matter which oxygen you want to share that a lone pair. Later on, when we discuss resonance structures, you will see that you actually would have 3 resonance structures for this NO3, but they are equal to each other. Okay, so that's why I said it doesn't matter which oxygen you want to share. Okay, all right, form a 1 double bond, and now nitrogen and 3 oxygens, they are happy, and we finished the step 4, and that's pretty much it, right? That's what we have for the Lewis structure of NO3 minus. All right, one more example. Now this one is a little bit different. Number 5. Okay. All right. Number 5 is SOF plus. Well, this is a cation. Okay, and it also has 3 elements. Well, if you happen to remember the electron negativity trend, if you rank the electron negativity of those 3 elements in an increasing order, that will be S, less than oxygen, less than fluorine. Okay. If you don't know how I get this, you need to review the topic number 1, electron negativity trends across the periodic table. Anyway, so this rank tells us sulfur would be the central atom. Sulfur, oxygen, fluorine. Okay, skeletal structure, single bond for each pair. Bracket and plus sign outside the bracket to indicate that this is a cation. All right, now the second step to calculate the total valence electrons. Sulfur, group 16, 6 valence electrons. Oxygen, group 16, 6 valence electrons. Fluorine, group 17, so 7 valence electrons. And it's positively charged. And according to the notes for step 2, if that is a cation, then you need to subtract the charge. Well, because this species has to lose that one extra electron to get stabilized. All right, so you have to minus 1 electron. Of course, this comes from that positive 1 charge. All right, if you get them together, you will have 18 electrons. All right, now 18 valence electrons for us to use. Again, you've already used part of them, but we still need to distribute the rest on the fluorine and oxygen to make sure they satisfy octets. Oxygen needs 3 more pairs to satisfy octets. Fluorine needs 3 pairs to satisfy octet. Okay, now if you double check, we have 8 here, 8 here. So you used 16 electrons. Okay, you have 18 available for you to use, and you used 16, so you have 2 extra electrons. You cannot put those 2 extra electrons on oxygen and fluorine anymore because they are happy enough. They cannot get more than 8 electrons. So we put them on the central atom. Because sulfur has only 4 before you put the 2 extra. It needs electrons anyway. And if you double check, sulfur has only 6, so but we've already used all of the electrons, right? 8 here, total 16. Plus 2, you have 18 already. So how about a double bond? Well, the problem is which side should have that double bond, on this side or this side? Well, the end of this charge, the fluorine will never form a double bond. Okay, well, why is that? Because fluorine has the highest electron negativity across the whole periodic table. It likes electron so much and it becomes so selfish. It does not want to share more than 2 electrons. In other words, fluorine will always form one single bond. Okay, that is why when we consider double bond, we will not consider fluorine. Instead, we'll have to consider oxygen. Okay, so oxygen will share 1 pair with sulfur to form a double bond. And now if you check, oxygen 8 electrons, fluorine 8 electrons, sulfur 8 electrons, everybody's happy, and this is the loose structure of this compound. All right, when you come to class, you will see more examples, and if you have any questions, let me know.